two examples of vector field. One vector field in 2 dimensions and one vector field in 3 dimensions. So what is the idea? What is the definition? What is the definition? Well, the definition is easy. It's a function in which you assign any point. Let me use here. Number 3 is better. X, y point. You associate with the, for example, any point here, one vector. And the vector, well, the vector is formed by, in this K2 function, P, X, y, Q, X, y. Who is PQ? Well, PQ are scalar functions. Scalar function. So basically is any point you associate one vector according to this mathematical relationship PQ que state this component, no? So for example, donde estamos clear, pero I suppose que es clear for me, in Hamilton notation, P, X, y, I vector, plus Q, X, y, J vector. Alright, entonces likewise, in 3 dimensions, is similar idea. We have any point in 3D. Of course, in 3D we have 3 components, no? X, y, z. And you associate a vector, but this vector is 3D. So we have the function P, X, y, z, Q, X, y, z. And the third component normally is called R, X, y, z. Okay, in the Hamilton notation, we have P, X, y, z, I, plus Q, X, y, z, J, plus R, X, y, z, K. End the story. This idea is clear or no? This idea is clear or no? Yes or no? Clear or no? Answer me. It's clear. Okay, cool. Now, the problem is, well, professor, the only thing I understand so far is that the vector field is a bunch of vectors. Okay, this is a good definition. So now, let's do it by curiosity. Let's do one sketch of the vector field by hand. But don't worry too much for this because we have application to do vector field in 2D or in 3D using computer, right? Okay, one elementary kindergarten example. Look, suppose I did a vector field example 1 and the one application, okay? I want to explain in a few seconds. Suppose I have this point in the field. I want to plot by hand the vector field, que es super easy. O sea, in this case, P is equal to and Q is equal 1. Okay, no depending X, no depending on Y. Entonces, ese vector field que es constant. And you, for example, you pick one point, arbitrary point here. And the component, the first component is P, is 2, and the Q is 1. Entonces, the vector in this case is like that. Because this is equivalent to saying any point, it doesn't matter, the position is the vector 2, 1, and the Hamilton notation is 2i plus 1j. So now my field is 2, 1, like that. 2, 1. This is easy or no? It's easy, right? Clear or no? Let's do it by curiosity. Let's do it by curiosity. Another more, a little bit interesting because this is look like a little bit stupid vector field, but let's do it. For example, another. For example, the official example one. Well, this is example one. No? Official es. Bueno, okay. Entonces you say, bueno, professor, okay. Entonces, what is the application that you say that we can do a vector field? Well, this application I want to show you now. Let me try. There are many applications. Basically, the application is using GeoGebra, no? Some application I create another node, another I copy for another teacher, no? Another mathematicians, and the internet is available, no? Entonces now, for example, do you see the vector field now, the application? Do you see it? Yes, okay. Suppose que I copy the vector field, que es 2,1, ¿no? The component is 2, and the other component is 1. You click here, click. Well, maybe you need to check it. There you go. This is the vector field. You see? This is the vector field. So now, any example that we're doing today, if you want to make to do the graph, we open this application. As this application I have personally, and I want to will send to you when the class is over with the video, and you experiment with this. No? You try to do your. It's super easy. It's a very intuitive idea. You only put the component bx, and in this case they call bx by, but it's the same pq, no? Pq, and this is only in 2 dimensions. We have another application in 3 dimensions, but no. The most important is in 2 dimensions. In 3 dimensions something, but no all of them. Okay, so let's come back. Let's come back to the first actually first example, no? Okay, cool. Okay, here, over there. Switching to, okay, cool. Okay, do you see my whiteboard now? The official example one is I suppose que is this. Let me see if it's this. No. Another 3. I call 3 in your moment, no? Okay, there you go. This is cool. Okay, super. This is example 3. I call on the picture example 3, but officially in my paper now is example 1. That's not important. Example 1. Now, example 1 es a vector field que es x, y. See, I did the sketch of the vector field using the application, you see something like that. It's completely like a radial. So from the origin, open in any direction, and increasing the magnitude, amplitude of the vector. No? Okay, this is an example. No? Now, to understand this, we have 2 operators. The first operator is the divergence. Okay. To understand the property for the vector field, we have, fortunately, two operators. The first one is called divergence. And so far, the symbolic way to the divergence div. So div of the vector field f is equal partial derivative x with respect to the partial derivative p with respect to x plus partial derivative q with respect to y. In another word, using another notation, partial del p dx plus del q dy. Okay, this, remember, in our example, this is p and this is q. Entonces, what is the interpretation of this? Let me try to explain using elementary example. For me, it's important when you compute something in calculus, you need to understand what is the meaning of that. It's super important. Compute that. Well, what the hell is that? Okay, diverge. What is that? Now, diverge is, suppose this example. Remember, I explained at the beginning, the last class. Okay, you apply this idea of the vector calculus in fluid mechanics and electromagnetism. Because fluid mechanics is a fluid. It's a vector field. Now, suppose that we have, this is the container, it's a bathtub. And this is the water. Water. Okay. Then we have here now let me try to do my best skill in drawing. It's a faucet. And this faucet put the water inside the bathtub. And here we have also, a drain. This is the drain. And one moment I open the drain and the water is out the bathtub. This sketch is super easy to understand. However, let me try to do a full floor plan of this. Okay, and this, we have a faucet, and the faucet look like a source of water. Okay, this is a source of water. Now the liquid fluid, the water in that case, fluid in this direction. And see, I open the drain. Well, the drain look like a sink. Okay, the streamline of the water here is coming but in this direction, source and sink. Similar idea, it's another example. In electromagnetism, you have two charge, electric charge. We have positive charge and you have negative charge. The positive charge, the string line of the electric field go outside the positive charge. However, in the negative, inside. Similar, analogous, it's the same idea. Therefore, the mathematical simulation, this idea, is, of course, same vector calculus. Now, let's come back to divergency. Okay, we define here, but I don't know what is the application of this. I have no idea. Well, when the divergence is positive, here, let me explain in detail this. When the divergence of the one vector field, divergency of the one vector field is positive, guy, in one specific point, at this point. Okay, remember this is depende x, y, sí, o si es en two dimension x, y. Entonces es source. Okay, here in that point, I suppose when I compute the divergency, at that point the answer is, I don't know, 20, positive. However, when the divergency is negative, it's a sink. And when the divergency is 0, it sometimes happen, frequently happen. For example, in this point, and 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 this point, we have no source, we have no sink. At that point, we have source. And this point, I have so the divergence negative. Here, positive, sorry. This is negative, and this is 0. And when this situation happens, well, this is the source free. This is one terminology, no? Source free. We have no source and no sink. Okay, this is the interpretation of the divergence. It's local property. Diverging that point, diverging that point, diverging that point, diverging that point. This is the interpretation. By curiosity, we take advantage this example, no? And let's see what is the divergence of this vector field. Que at the beginning was x, y, no? X, y. Well, divergence of this vector field is partial derivative p with respect to x plus partial derivative q with respect to y. This is p, partial derivative p with respect to x and y, and partial derivative q with respect to y is 1, and 1 plus 1 is 2. And 2 is a positive number. That means in any point in this vector field, we have a source. You know, it's weird, professor, because it's a source in any point. In this example of the bath 2, we have only one here. Well, the problem is that you see in this vector field, so you are, for example, you want to analyze the divergence in one specific point. Remember, divergence is a local property. The local means que es in one specific point, no? You are doing, for example, a little bit, a small circle. Not necessarily circle, any closed figure. Maybe square, maybe circle. And you see que the vector que get in is smaller than the vector que go out. This happens in any point here. That is a reason can this diverge positive in any point. Clear? 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 Do you follow me? A ver, clear. Okay. Okay, Álvaro. Entonces now, that's it. No. This is just the beginning. We continue with this example. In this example, I want to erase that part. In this example, okay, let me erase that part. You know the meaning of divergence. We have another operator. Let's call it. Okay, entonces to conclude that part, what is the meaning of divergence? Well, the divergence measure the net flow out the point. Okay, is net flow out the point. Okay. We have another operator que is called a curve. Wow, what is that? A curve. It's another local property. Another local property. Entonces, what is the formula, professor, for the curve? Well, the curve of the vector field F is in two dimensions partial derivative q with respect to x minus partial derivative p with respect to y. This is definition in 2 dimensions. In 3 dimensions, it's different. I want to explain you a moment today, of course. Entonces, now, when you compute that, bueno, let's do it. Is partial derivative q. Q is y. In this example, partial derivative with respect to x is 0, because we have no x, minus partial derivative p with respect to y, we have no y, is 0. 0 y 0 minus 0 is 0. What means que the core is 0? It's 0 because our vector field is irrotational. Because the core, guys, give me a mixture of the rotation of the vector field. In this case, you see that this vector field no rotate, no rotate. It's completely radial. Okay, rotation is when you see. Let me explain the idea. Suppose that the curve of the another vector field, not this is 0, is positive. Okay, entonces the interpretation of this is que this vector field in this specific point rotate counterclockwise. And the way to see that, is we put in the ending point, guys, a device like that. Whoa, like that. I don't know, say 4 or 6 side, que es the paddle wheel. So you put this paddle wheel in one specific point in this vector field. Look. And for sure, I guarantee you that this is irrotational. No rotate this. No. Why no? Well, because I suppose that this paddle field, suppose that we have 1, 2, 3, 4, 5, 6 paddle. Suppose that the vector field is hit in this direction and in this direction. And it's the same. Entonces, es obvio que no rotate. It's irrotation. And let's see the implication for to be irrotation. But let me finish the idea. See this rotate in that direction because I suppose that this vector field is specific. You see another example I promised today. Okay, short is shorter here. So this is bigger and create a torque and rotate in this direction. Entonces the curve is positive. Esta interpretation. If the curve is negative, entonces rotate clockwise. Okay? So we discover a new operator curve que give me idea que the vector field is irrotational or no, or rotate. Let's see another example. But before to finish the example 1, this is important detail now. This is the most important thing I want to explain today. Since irrotational, this implies that our vector field is conservative. And what means to be conservative? Mathematically speaking, conservative is that any vector field gets irrotational. You can find one potential function. Yeah, I promise, guys, that we are doing 1,000 examples of potential function. Okay, compute potential function. So first of all, you compute the curve of the vector field. 0. Wow, good. It's irrotational, and now it's conservative. And conservative means that we can find potential function. What is the formula? What is the idea? What is the strategy? Okay, this is the strategy is that the vector field, this vector field, come from for the gradient of the one phi. Phi is a scalar function. Phi is potential function. Now, to find the potential function is super easy, because you take, for example, the vector field in general PQ, you, for example, find the anti-gradient. You are familiar with the antiderivative, right? But this case, anti-gradient. Anti-gradient es exactly antiderivative, pero component by component, ¿no? Entonces, yo suppose que, for example, suppose que P come from for the partial derivative phi with respect to x. And likewise, Q come from for the partial derivative phi with respect to y. And who is phi? Phi is the potential function. Okay? Entonces now, si I want to get the potential function, you apply integration in both components. Anti-gradient is a technical name of this. So you take, for example, in this example, get our example, remember, P is x and Q is y, no? In this example. Entonces it's easy, for example, if you want to find potential function, x comma y, you integration P with respect to dx. Let's do it. Is x comma y, P is x, integration x dx, nice. This is x squared over 2. Plus c, no? But in this case, no c. No. It's because actually the thing we're doing is solving a differential equation, but partial differential equation. And the partial differential equation is different to the ordinary differential equation. But don't worry too much for this. S is something plus something I don't care. But this something dependent on the y. So it's a function, but depending only of the y. For example, so you are doing backward. So you are differentiate this potential function with respect to x. Let's do in backward. Is these two go to the front, subtracting 1 here, plus derivative this with respect to x 0. Entonces now, in this case, you suppose que es the function, not the constant, like a cal 1, but this function depends of the another variable that do not participate in the integration. So you integrate with respect to x, it's a function of fy, arbitrary. Okay? You don't worry too much because I want to explain the procedure to find this in 1 second. Likewise, well, I did using one component, but I can do using another component. Suppose que hay integration Q, que Q en our example es y dy. Okay, entonces es y squared over 2 plus another arbitrary function que depending of the variables. Entonces you don't worry too much for this because you put together. Actually, our potential function is x squared over 2 plus y squared over 2. End the story. Maybe suppose let's do it backward. Suppose que I give you that function que es scalar, no? I say you compute the gradient of this. Okay, no problema, I try. I know the definition is partial derivative phi with respect to x, comma, partial derivative phi with respect to y. Let's do it quickly. Partial derivative is with respect to the phi is, let me see, with respect to x is 2sx. Partial derivative with respect to y. Do you see that we come back at the beginning? So one application of this new thing we study, the potential function is, well, you can, for example, do the graph of this. Do the graph of this. The graph of this potential function in the plane xy. You see the potential function as a family of the circle. So this is equipotential. Bueno, suppose que potential function is equal to 1. Entonces it's a circle with the radius is square root 2, and so on. It's a family. So for this potential function, and you can interpret this family of the potential function like a level curve. Therefore, you know very well that the gradient is orthogonal in any point of the level curve. So si I want to do the vector field by hand, well, one possibility is do the sketch of the potential function, different potential function, and you put here orthogonal, perpendicular, in any point, our vector field. I promise that I want to explain in detail the application of the potential function in your moment, en detail, pero no now. Entonces, si I want to summarize everything, conclusion. Because we are doing in the example 2, 3, 4, and 5. I bring 5 examples today. So we have 2 operators to analyze the vector field. The first one is divergence. Divergence give me the information about the how much net flow go out to the point, no? Maybe positive, it's because it's more flow out than in, or negative is a completely opposite, no? And 0 is source free. And the curve give me the information about the rotation. So suppose now that we have a hurricane, and the hurricane vector field, you see que es rotate. Entonces, when you compute the curve, give me positive or negative, depending on the direction of the rotation. When the curve is 0, it's the most important vector field. It's because it's conservative vector field, and you can associate, compute that using anti-gradient, the potential function. And the potential function so far give me information a little bit of the vector field. Okay, let's do one more example. I have several examples. Wow. Okay, everyone follow me? Look like we are, I suppose. But little by little, you adaptate to this language, you know? Okay. Potential function, is rotational, divergent curve, and so on. Okay, let's move on to the next example. Next example, I suppose que 4 in the picture. Let's see, 4 in the picture. Okay, no. Let me come back again to the application. What application? The application of the vector field I showed you before. Okay, switching to this application. Do you see the application? I want to investigate the example first, que es X here and Y here. Do you see or no? Do you see the... yeah, bottom. Okay. Let me see, something's wrong here. X and Y. Yeah, there you go. Do you see the vector field is totally radial, no? Now here is amazing. They give me the answer for divergence gets 2 and the curve is 0. So irrotational, of course, conservative field of course, we can compute the potential function, and the potential function in this specific example is a family of the circle, and the vector field is completely perpendicular, no, to the tangent. So we have circle, you have the tangent vector, and this is no tangent, it's a normal vector, it's a perpendicular. Another way to visualize this application is fantastic because it gives me information about the animation curve and divergence with animation. Look, this is the the point I want to select. I drag, and in animation, look at that, what happened. Animation curve, animation. Wow. What are the interpretation of this? You see in this point, the divergence is equal to, no? Totally independent of the point I select, it's always 2. Entonces, it's source. And you see how flashing, and I suppose it's pink color, no? In pink color, entonces now you see that this is a source. Divergence positive is a source. And this is completely irrotational, no rotate in any point. That is a reason that this vector field is conservative. Cool? Cool? Okay, let's come back to our whiteboard. Okay. Do you follow me, guys? It's important to me understand that you follow me, no? Okay, Max. Okay, Max. Let me try to bring another example. Okay, suppose get the picture number 4. No, I saw number 3, number 4. Number 4. That one. Okay, not good. Sorry. No, it's not exactly I want. GUI device 4, 5. Maybe this. No. Okay, don't worry. Let's do a number 4. All right, number 4. Doesn't matter. Okay, minus y. Okay. Okay. Example. This example. Let's do it. Why not? Okay, I call example 2, no? Okay, example 2. In this case, the vector field is minus y, comma x. Okay, it's given. This is P and this is Q. To compute the divergence, que es operator que help me to understand the behavior of the vector field, is px plus qy. Okay, entonces when I compute that, derivative p with respect to x is 0, and derivative q with respect to y is 0. Oh, 0, 0. Entonces this is no source, source free, this vector field. But you see this vector field look like hurricane, no? Look, this vector is in this direction, this vector is in this direction, this vector is in this direction. So maybe when you compute the curve, we have a numerical value, no 0. This is no conservative. This is no conservative vector field. No. Differentiate this, differentiate this, differentiate. Okay, differentiate. The formula is qx. You need little by little. You are familiar with the formula for the curve and the divergence. Okay, partial derivative q with respect to a1. Partial derivative minus. The formula have a minus. Partial derivative p with respect to y is negative 1. Double negative become positive. 1 plus 1 is 2. In this case, yes, that you discover mathematically that our vector field rotate counterclockwise in that direction, exactly that. And this number, what mean that number, guys? This number indicate the angular velocity divided by 2. Don't ask me why, because the proof is a little bit complicated, but it is not important. The important is rotate or not rotate. It's important. Entonces now, obviously, si the core is not zero, this is a non-conservative vector field. Therefore, we have no potential function. No potential function. It's important, guys, to understand. If, for example, we study definition vector field. Okay, vector field is this circle indicate the set of the vector field. However, one subset special of the vector field is conservative. Conservative vector field. So inside this special vector field, we can compute the potential function. Outside, no. So this example here, it's a vector field, cool, but the potential function do not exist because it's not conservative. Cool? Do you understand the idea a little bit? One more example. Let me see in the application how the curve is 2 and rotate. Sorry, I need to switch in the whiteboard, application, but it's important that you understand very, very well this. This is the foundation to the whole thing we are studying in vector calculus. Let me try. Okay, application. Do you see the application? Do you see? Okay, I want to change the vector field. Now it's here negative y, and here positive x. Okay, analyze, no complicated, easy vector field so far. Okay, look at the hurricane. Now, in the animation, you see at any point I put here local property, divergence 0. So no source free, no source, no sink. However, in any point you put the paddle wheel, rotate curve equal to counterclockwise. It's cool or no? And after, I promise, can you see the application of everything? This is just the beginning, the foundation to understand vector calculus. And you see here divergence 0 and chorus 2. Understand or no? Do you see the rotation or no? Clear. Wow. Let me switch into the whiteboard now to see another example. Okay, erase everything. Now another example. I suppose it's example 5. I guess so. I am lost, totally lost. Example 5 maybe. Let me see. Oh yeah. Is I did that or not? No. Okay. Let's do that. Example 5. Example, okay. I call 3, no? Okay, example 3. Example 3 is vector field que es negative x, y. Okay, cool. In this case, let's compute divergence of this vector field. It's a big I and it's a Q. But in that case, remember the formula for divergence: P partial derivative with respect to x plus partial derivative Q with respect to y. In that case, partial derivative p is -1 plus partial derivative q with respect to y positive 1 is 0. Again, we have a source free. And the curve, well, the formula for the curve is partial derivative q with respect to x minus partial derivative p with respect to y. In this case, partial derivative q with respect to x is 0, and partial derivative p with respect to y is also 0. Wow, it's conservative. But this is more special because it's conservative and solve-free together is called fluid mechanic potential flow. Potential flow. Potential flow is completely free vector field. Okay, we analyze in the middle. Remember, in the bath2 you have here the faucet and the sink, and that part is important, this vector field. But in this case, both are 0. The divergence 0 and the curve 0, no rotation. And it's conservative, and we can, of course, apply the potential function. Okay? Okay. Let me try to investigate this special. This is more special. That is conservative, but it's solve-free. And together, it's called a potential flow. They promise when you study fluid mechanics, you see this potential flow, potential flow, potential flow. My goal is give you the mathematical tools to understand this subject. Okay. Now let me try to show you. No too much complicated with the potential function. No. It's only to see in the application. This example is minus x, comma y. Okay, in this case, look. Okay, let me share the screen to the application. Okay. Do you see the application? Okay, I want to change. This is minus x. And positive y. Oh, weird. No, not weird. Let me see. Okay, in this case, you see that both are 0. The curve is 0, and divergence is 0. So now it's irrotational. We have the potential function. We can compute the potential function. Also is no solve-free. See, solve-free and conservative together is potential flow. Do you see? Let's see another example. Now let me see. Okay, this guide, I suppose. Okay, no, not here. Oh yeah, deal. Okay. Another example. I come back to the whiteboard and let's see that. Okay, whiteboard now. Okay. I suppose you see whiteboard, right? Okay, suppose one vector field is the last example, number 4, no? Example 4. Example 4, suppose I have the vector field. You can put the argument x comma y because we are working so far in two-dimensional. And the vector field, the first component is 0. But the second component is a weird function. It's minus absolute value x plus 4 divided by 4. Okay. That is a reason I complicate this. No, because I want to illustrate one thing in this specific example. And we compute, for example, the divergency of the vector field. Okay, the formula is P partial derivative P with respect to x plus partial derivative Q with respect to y. Es obvio que es 0. 0 is 0. And the Q component do not depend on y, is 0. One more time, we have solve free. Okay. However, the curve, no surprise. Curve of f. The formula is partial derivative q with respect to x minus partial derivative p with respect to y. Partial derivative q with respect to x, it's a little bit weird. It's like derivative with respect to x of that function, que is minus absolute value x divided by 4 plus 1, no? Because I split this common denominator. And the derivative of the absolute value function, I don't know. But I remember something. For example, absolute value function by definition is one piecewise function. You can suppose like that. And which is equal x if x is positive or 0. So don't change the sign because absolute value 3, you know it's 3. However, if it's negative, you change the sign if x is negative. This is the formula, no? To compute the absolute value. If you differentiate that, it's easy because in piecewise function, you differentiate one piece by one piece. For example, you differentiate x with respect to x is 1. You say equal 1 if x is greater than or equal to 0 and negative 1 if x is negative. Okay, and so now you can write like that. Yeah, you can write like that. You can write like that. Or you can write like that. Look, this function, sometimes called sine function x, because it's a special function. Okay, when the x is positive, the value is 1, and when the x is negative, the value is negative 1. Entonces this is equal, minus the derivative minus. I dedicate to differentiate only the actual value. A sine function of x divided by 4, and derivative 1 is 0. So this is the formula for the curve. The curve have different sign depending in the quadrant. No? Suppose that you have in the first quadrant, in which the x is positive. Any point here, the curve is negative, does it rotate clockwise. However, when the x is negative, rotate counterclockwise, because when the x is negative, entonces sign negative numbers, negative 1, negative together positive, entonces rotate clockwise. Here, exactly the same, because depending only the x. And here, exactly the same. This is one idea of the vector field. I want to show you in the application. This application default have a specific interesting example. Okay, I hear. Go. Boom. Okay, look at that. I copy this example. So this vector field is not here, so in the application, the default bring me the application. Example que bring me the application. B component x p is 0 and q is this. And divergence 0 to any point, solve free. And the curve no. The curve is a function and depending the x. The negative absolute value x divided by x is a sine function, sine. And you see how rotate. Rotate, in this case, rotate clockwise. In this case, rotate counterclockwise. In this case, rotate clockwise. In this case, rotate counterclockwise. A little bit confusing or clear? A little bit confusing or clear? Clear. Cool. Now, let's move in now to the 3-dimension. Because I am boring to do the problem in 2-dimension. 2-dimension, 2-dimension, 2-dimension. No, what is the formula, professor, in 3-dimension? Okay, 3-dimension now. 3-dimension now. Okay, in 3-dimension we have vector field, so curve and divergence. This is the idea now, curve and divergency in 3D. Now, okay, what are the, well, we have vector field x comma y comma z, and normally the function is pqr, p comma q comma r. That is a scalar function depending of x comma y comma z. To do short, I omit the argument, no, que es x comma y comma z, no, and here exactly the same. Divergence by definition is similar. Partial derivative p with respect to x plus partial derivative q with respect to y plus partial derivative r with respect to z. Boom. And it's obvious, it's important to understand that the divergence is a function depending of the variables. Of course, it's a scalar function. However, the curve, no. The curve in 3D is a vector. It's important you understand. In 2D, the curve is no vector, it's a scalar. In 3D, yes, it's a vector. And this vector, the definition is a little bit complicated. The first component is r, partial derivative r with respect to y, minus q, partial derivative with respect to z, comma, pz, minus rx, comma, qx, minus py. But nobody memorized this formula. No. I propose you doing this formula like a cross product in the notation. So now, pay attention, que this is very, very abstract. No complicated, but abstract. Okay, I suppose que you remember this operator, que es the operator que we use in gradient. Entonces, this letter is some book call it del, and some book call it nabla. So historically, some mathematician call it del, and another is nabla, but it doesn't matter. When you call del or nabla, everyone understands it's the same thing. So this is symbolic. You suppose like a vector, que es partial, so del x, comma, del y, comma, del z. Professor, but this is crazy because the partial derivative, but we have no here, nothing. It's symbolic. It's totally symbolic. But the symbol is very, very convenient. I want to show you why. So now you this formula, can nobody remember this. You use it like a determinant, similar to the cross product that we were doing before. This is famous I, JK. You copy here del, que es partial derivative x, but partial what? Partial, I don't know. Partial derivative y, partial derivative with respect to z. And you copy here PQR. And when you're solving this, let's do it quickly. In the way I want, suppose the component I equal is, you delete mentally this and this, is partial R with respect to X. Do you see? Minus partial Q with respect to Z. Wow, exactly the same of this. Minus J. Boom, boom. Partial derivative R with respect to X minus partial derivative B with respect to Z. Bueno, professor, pero this is completely different to this. Well, the difference is because it's minus. It's minus does affect everything. Plus K, and the K is partial derivative Q with respect to X minus partial derivative P with respect to Y. Okay, by the way, this formula you are familiar. This is the curve in two dimension formula. Because actually, in two dimension, it's the same formula, except que the curve is a vector, pero es perpendicular to the y-board plane, que es K. I suppose XY, I in the same direction of the x-axis, J in the same direction of the y-axis, but K, where is K? K is perpendicular to the y-board. This is the reason. Okay, now, the most important moment now. Using this symbolic operator, we can write, for example, del or naula, the way you prefer to call, out. Naula dot product F. What is that? Bueno, this is easy. Look, naula is this. Partial derivative X. So, of not, I don't know. Partial derivative, I don't know, with respect to Y, comma, partial derivative, I don't know, with respect to Z. The product and the vector field is a vector PQR, no? You perform the dot product. The answer is partial derivative P with respect to X. Look, this partial derivative apply in the first component. This apply in the second component, and this apply in the last component. Is partial derivative Q with respect to Y plus partial derivative R with respect to Z. Wow, and this is the divergence. Look at that. Okay, there's one fantastic notation every mathematician and book using is the del operator dot product F and divergence. And this is equivalent to this. Divergency of F is equal nabla dot product F. Likewise, a curve of the vector field S is a cross product nabla cross product F. It's no surprise because we are doing here, right? No surprise because we are doing here. And but I have more because well, no. The first time I see the del or nabla operator was in the gradient. But in this case, no dot product and no cross product. It's just the regular multiplication, no? Entonces now, suppose you have partial derivative with respect to x, comma, partial derivative with respect to y, comma, partial derivative with respect to z, and now here we have a function f, no vector field, it's a function f, que es a scalar function, and it's a regular multiplication. Entonces, si es regular multiplication, es a vector que es partial f with respect to x, comma, partial f with respect to y, comma, partial f with respect to z. And this is the definition for the gradient. Wow, fantastic. We summarize using del or nabla notation the most important operator in vector field. divergency, curve, and gradient. Gradient is just multiplication, and divergence is a dot product, and curve is a cross product. Okay, so now to see the beauty of this, let me try to investigate two important identity that we study throughout the, or we use it throughout the vector calculus. Okay, do you follow me? Do you understand the notation, guys? Do you understand the convenience notation or no? Using the cool max. Okay, let me try now to prove some identity. For example, see, I want to compute divergency of the curve of the one vector field. Using the new notation. This is the del dot product del cross product F. Entonces, let me try to understand. At the beginning is giving a vector field, PQR. Suppose in 3 dimensions. It's a vector field. Vector field. When you compute the curve, please give me another vector field, because you know the curve in 3 dimensions is a vector field. And when you compute divergency of this vector field, we have a scalar function. Okay? But the thing I try to prove, okay, this is equal to 0. It's doing. And logical makes sense or no? Remember, suppose we have vector field, but when you compute the curve of the vector field, I suppose we have no source, it's source free, and the range source free is 0. Okay, it's one interpretation. Let's do it. For example, technically, I suppose F is a vector field PQR. The first operation I should do is compute the cross product del cross product F. Double arrow, no? The arrow of the operator is IJK. This is symbolic. And it's a PQR. I did before that. The answer is I RY minus QZ minus J RX minus PZ plus K QX minus PY. It's the component, no? Now I want to this vector field, on this vector field is RY minus QZ, comma, PZ minus RX. I interchange the sign here, but the negative we have outside, comma, QX minus PY. My goal is this is a vector field, but this vector field is not F. This vector field is a curve of F. Now I need to find divergency. And divergence is super easy because the definition for the divergence is you take the first component and differentiate with respect to x. You take the second component and differentiate with respect to y. And you take the third component and differentiate with respect to z. This is the definition for divergence. The divergence of the curve f is equal. Now you differentiate with respect to x. This component entonces es ryx, second derivative. Actually, we are doing the derivative with respect to y first, and you are doing now secondly with respect to x. Minus QCX. Done. Plus derivative with respect to y is PCY minus RXY plus partial derivative Q with respect to XC minus partial derivative PYC. Wow, and this is cancelled with that. And this is cancelled with that because you know the order is not important, and this is cancelled with that. And the answer is C. Conclusion. This identity we're using not every day, but we're using frequently. Okay, so divergence of the curve is nothing, is zero. Is zero. And also another important identity. Let me separate this. Suppose this, the curve of the gradient of the function f is zero vector. What means zero vector? Zero vector means the vector 0, 0, 0, no? In 3D. Okay, let's compare the gradients. And the convenient notation, del notation is cross product is a curve of the del multiplication by f equals zero vector. Okay, let's compare del first. Del, so the gradient. The gradient by definition is partial with respect to x, comma, partial with respect to y, comma, partial with respect to z. F is the hypothetical scalar function. And you compute the gradient, bam, and you get the vector. It's a vector field, of course, because it's variable, depending on the point, no? However, when you compute the curve of this, it's doing a curve is the famous cross product. Is the symbolic notation, no? And here we have the component of this vector field is fx, fy, and fz. It's doing. Okay, the component I is partial derivative is f cy because you differentiate in the gradient part with respect to the c. Now you differentiate now with respect to x minus f y z. In this case, look at it. Is you differentiate with respect to y first, and now you differentiate with respect to z. And you know that this is the same. So this is 0. Wow, it's gone. 0i. And likewise, you can verify minus j f c x minus f x c is 0j. Okay, exactly the same as f yx minus f xy. 0k. Okay, there's an interpretation of this idea. Suppose you have a scalar function f. Cool. You compute the gradient. This gradient is a vector field. By the way, any vector field can come from for the potential function, in this case f is the potential function, is conservative. When you compute the curve, it's 0. It's obvious, right? It's obvious or not? Okay, let's dedicate the rest of the time doing at least one decent example of the potential function. Okay. Okay, let's do an analysis, total analysis, divergency, curve, and potential function. Okay, in the promise, in next class, we see the application of the potential function. Okay. This is the last example. Look, suppose you have vector field. This vector field is in 3 dimensions. And the formula for PQR is given. is y squared z, comma 2xy c cubic, comma 3xy squared c squared. Okay. Question number 1. Compute divergency. Compute divergency, the vector field. And this notation, remember, is nabla dot product f. The formula is partial derivative p with respect to x, partial derivative q with respect to y, partial derivative r with respect to c. This is PQR. PQR. Partial derivative p with respect to x is 0 because p do not depend of x, plus partial derivative q with respect to y, well, we have only one y, and derivative y with respect to y is 1. And I stay the other guy to xc cubic because you consider constant, no? And r with respect to c is 6 xy squared c. Okay, and this is my divergency. Now the product f of this vector field is 2xc cubic plus 6xy squared c. You want to investigate this in detail, you go to the application in 3 dimensions, get the R application in 3 dimensions, you select the specific point. Suppose in the test I ask you, what is the divergence at the point 0,0,1? Well, you plug it in. This is easy. X is 0, Y is 0, C is 1. Plugging in, but in this case it's 0. It's 0 because 0 times something, 0 times something. Okay, it's not happy example, but it's okay. Okay, the important thing is that this is a scalar function. The divergence is a scalar function. Okay, number 2. Compute the gradient. The curve, sorry. The curve. The curve and the other notation is nabla cross f. Entonces, IJK, symbolic partial derivative. This is totally symbolic, guys. It's a mnemonic device that the mathematicians create to understand that part. And we have here PQR. Who is PQR? It's y squared z, 2xy z cubic, and 3x x is xy squared c squared. It's doing. I like this organization, guys. You copy I, always, paréntesis, paréntesis, minus j, paréntesis, paréntesis, and k, paréntesis, paréntesis. Okay, entonces now delete this mentally and you differentiate this with respect to y, que es 6xyz squared, minus, differentiate this with respect to z, well, again, is 6xyz squared. Wow, it's 0. 0i. Likewise, I don't want to repeat this, but it's easy to understand. It's 3y squared c squared minus 3y squared c squared is 0j, and 2yc cubic minus 2yc cubic is 0k. Therefore, I discover that the curve of this vector field is given in this example in 3 dimensions is 0, 0, 0, que es 0 vector. Therefore, our vector field is irrotational, no rotation, que is equivalent to say conservative. And when it's conservative, we have potential function. Okay, you see the application in the next class. But let's do in the potential function. How you find the potential function? Easy, easy, easy. You compute the anti-gradient, que es antiderivative component by component. For example, phi, que is the name of the potential function. I don't know why, using the Greek letter. X, y, z. Es the integral antiderivative p with respect to x. Phi, x, y. Es the antiderivative q with respect to y. And phi, x, y, z is the antiderivative r with respect to z. Well, professor, but we have three potential functions. No. Let's see how. When you compute the antiderivative of the first component, que is at the beginning, look, y squared z dx, you consider que everything is constant. Entonces, basically, we have x, y squared z, correct? Plus something que I don't care. Never, I care. It's a function, but I don't care. When you compute that, the antiderivative of this is 2xy c cubic, but you differentiate now with respect to y, antiderivative with respect to y, we have y squared divided by 2, and the 2 is cancelled, does stay x, y squared, c cubic, no? By the way, I forgot here. No, I don't. C cubic. A ver. I make a mistake, carajo. Well, okay. Don't worry, I fixed the mistake. I copied wrong the vector field at the beginning. However, I fixed it because not necessarily it's exactly the same. This is cubic. Plus something. And the last one is antiderivative r. Who is r? R is 3xy squared c squared dc. This is what dy. Okay, this is antiderivative. Okay, entonces es c cubic divided by 3, the 3 is cancelled, entonces está xy squared. xy squared c cubic, ¿no? Beautiful, c cubic, plus something. I did analysis, guys, everything except that part under the consideration. The mistake is this, cubic. And the original problem. Look, I did well because it's cubic. But this is this. Okay. So now this is cubic. Everything is cubic. And this is my paper. So now, in this case, what is the potential function, professor? Well, the potential function is the collection of any function that you get when you compute the antiderivative component by component. In this case, it's a coincidence que es the same, but not necessary. Suppose in another example that you see next class, I promise, you see different function, you take everything put together without repetition. So the potential function in this case is x, y squared, c cubed. End the story. Cool? Do you follow me? Okay, I need to repeat something. Cool. I need to repeat something. Okay. Any vector field is given in the problem. You need to prove that the curl is 0. If the curl is 0, it's conservative. If it's conservative, you can find. So the potential function exists, and you can find use anti-gradient. Otherwise, no. Si the curl is not 0, entonces actually it's non-conservative field. Therefore, we have no potential function. Okay. Potential is conservative field is special. Pero fortunately, we can find in the real life potential function. For example, I suppose you took physics or no? You took physics. Yes, I suppose you remember potential energy. Yes or no? Potential energy, que es mgh, gravitatory potential energy. This is a potential function. Why? Because the vector field of the gravity is conservative. Okay, suppose que this is the surface of the Earth, our planet. Entonces we have different points. Bam, 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 bam. Entonces the vector field is like that. The vector field is, and what means the vector field? Guys, the vector field is a vector. Entonces the vector maybe is acceleration, is velocity, momentum, either way. But in this case, gravity. Okay, it's ng, no? Ng. And the vector field in this example is 0, minus ng. Yes or no? Ng. No h. No h. No h. Let me erase the h. Es minus because it's point down, no? This is the xy axis, no? Two dimension. Compute the curve of this. Compute the curve. What is the formula for the curve? The curve is this is p, and it's a q, no? The curve of this vector field is qx and py. Partial derivative. Bueno, ese consta, es obvio que es 0. Es obvio que es 0. Es obvio que es 0. And we have the potential function. And the potential function is, when you integration, for example, antiderivative p with respect to x. Y antiderivative q with respect to y. Entonces, pero p es 0. Antiderivative 0 dx es consta. O the constant que I don't care. However, when you integration q, que es minus ng dy, and between, I don't know, 0 to h, well, no necessary. Antiderivative, no define integral. Es obvio que es minus ng y, no? Y is the high in any point. This is the high. In physics, the professor don't call y, don't call h. And this is the potential energy in this point. Do you see the analogy? Little bit. No, not too much. I don't want to complicate too much. Do you see it, right? Entonces, in the last minute, I want to explain what is the reason it's conservative. Conservative. Because that means that the energy que dice potential energy, o sea, basically, the potential function in this example is the potential energy, gravitatory energy. Suppose that you are doing, I want to compute the work done when you're moving in this direction, to the point 1, to the point 2. What do you think about the work done by the gravity? Is positive or is negative? Work is positive. The work is positive in this trajectory. What do you think about the work done for the point 2 and the point 3 in this direction? 0. Very well. Work 0. What is the work done for the point 3 to the point 4 in this direction? -1. No, -1. Negative. No, -1. It's negative. And the work done, and this is 0 again, right? Work is 0. Do you see that this vector field conservative because the energy, for example, get spent my muscle to do the work in this direction, now the gravity return to me in this direction. In other words, the work done in one closed trajectory is zero. This is the reason que es conservative. Entonces I promise que we study in detail next class the idea for the conservative. We using the local property curve divergency to study global property of the vector field. Okay? Okay? Remember, send me the test today. Get the due date. Cool? Cool? Bye-bye, guys.